Hello, this is Richard Hammack's Calculus 1 course. We are in part 3 of the course on derivatives. Today, lecture 27, Implicit Differentiation. Implicit differentiation is a technique that we use to find derivatives when we are dealing not with a function relating x and y, but rather an equation relating them. And I'll explain what I mean by that on our first slide. With all of the rules we've developed so far, we can now differentiate just about any function that comes our way. For example, y equals f of x equals x squared minus 5. Here, y is a function of x. Given an x, you can find a definite y value corresponding to it. We might even say y is an explicit function of x. And we can find its derivative. By contrast, consider the equation x squared plus y squared equals 25. It has a graph. Its graph is the set of all points x, y on the plane that satisfy the equation x squared plus y squared equals 25. That means the x coordinate squared plus the y coordinate squared of this point equals 25, or 5 squared. And by the Pythagorean theorem, that means the point xy is a distance of 5 from the origin. So the graph of the equation x squared plus y squared equals 25 is therefore the set of all points at distance 5 from the origin. So it's the circle of radius 5. This graph is not the graph of a function. Unlike the parabola over here, which satisfied the vertical line test, this graph fails the vertical line test, so it's not the graph of a function. We can find derivatives of functions, but we don't know how to find derivatives of equations. Here, y and x are related by the equation x squared plus y squared equals 25, but unlike the previous situation, y is not an explicit function of x, and it's not clear what the derivative would be. You can talk about slopes of tangent lines to the parabola, and the derivative gives those slopes. You can also talk about tangent lines to the circle. What if we wanted to find their slopes? We don't have a way of finding a derivative. So this is the kind of thing that we're going to be dealing with today with implicit differentiation. We'll make sense of what the derivative should be in this context, the context of an equation and not a function. To further develop that idea, note that there are lots of functions, y equals f of x, that satisfy the equation x squared plus y squared equals 25. That is, if you substituted f of x in for y, you would get the equation x squared plus f of x squared equals 25 holding. One thing you could do is just take the graph of this circle and erase the bottom part. So I've indicated that in green here. Just look at the top part of the function, or the top part of the circle, and call that a function y equals f of x. And that passes the vertical line test. So it's a function. It's a graph of a function. Alternatively, we could erase the top part of the circle and just look at the bottom part, and we would get a function y equals f of x, a different function from the one we had here. Or perhaps you might want to get creative and mix and match, have a discontinuous function y equals f of x, whose graph lies on the circle. So it satisfies x squared plus f of x squared equals 25. This green graph that I've drawn here also passes the vertical line test, so it really is the graph of a function. And as you can see, you could come up with all kinds of functions, y equals f of x, that satisfy x squared plus f of x squared equals 25. And such functions f of x are called implicit functions of the equation x squared plus y squared equals 25. They're not really inherent in the equation x squared plus y squared equals 25, but they're implied by them. You could create such functions by erasing parts of the graph to get something that passes the vertical line test. These are implicit functions of the equation. So in a nutshell, today's goal is going to be to learn how to differentiate implicit functions, the ones that are illustrated, like the ones illustrated here. And this technique of differentiating implicit functions is called implicit differentiation. For a motivational example of this new technique, consider the graph of the equation x squared plus y squared equals 25. As we just discussed, this is a circle of radius 5 centered at the origin. It consists of all the points x, y that satisfy the equation x squared plus y squared equals 25, and in particular that includes the point 3 minus 4, shown here, because 3 squared plus negative 4 squared does equal 25. The question we're concerned with here, in this example, is to find the slope of the tangent to the graph at this point, 3 minus 4. So right here at this point, there's a tangent line, and the question is, what is its slope? Well, to find slope, we need a derivative, and to find a derivative, we need a function. So let's take an implicit function, y equals f of x, that passes through this point. We'll erase all of the graph except this portion right here, shown in green, and that's an implicit function, y equals f of x. And we're looking for the slope, m, of this tangent line. That would be f prime of 3, because f prime gives the slope at x. F prime of 3 would be the slope of this tangent line. That's our strategy. We'll take this implicit function, y equals f of x, as shown here, and the answer will be f prime of 3. So in order to carry out that plan, we need to first of all find f prime of x. And let's think about that. One way to proceed would be to solve the equation x squared plus y squared equals 25 for y and get y equals f of x. So doing that, y squared would be 25 minus x squared. So y is equal to plus or minus the square root of 25 minus x squared. And we take the negative of that square root because these are negative y values down here for f of x. So you get y equals negative square root of 25 minus x squared. And you could take the derivative of that using, say, the generalized power rule, and you would be able to find the derivative f prime and plug in 3 and you'd get the slope. But that's not the way we're going to proceed here, and the reason is that for most examples that we're going to look at, we're not going to be able to solve the equation for y the way we could here. Sometimes it's just not going to be possible. So we're going to proceed to find f prime of x in a slightly different way. We'll work this way. Start with the equation x squared plus y squared equals 25 that the problem is about. Look at this implicit function y equals f of x. For this green portion of the graph, y equals f of x for all points x, y on the graph. So plugging in the f of x to y, we get x squared plus f of x squared equals 25. That's just for this little green portion of the graph. But that's the portion we're concerned with. Look at what happens here on the left, where previously there was an x and a y. Now it's all x's. On the left is a function of x. And it's equal to 25, which is a constant function. Think about that as the function 25 plus 0 times x, we have a function of x on the left equals a function of x on the right. So we could take the derivatives, d dx, of the left and the right, and those derivatives would have to be equal. And let's carry out that plan. The derivative of the left-hand side equals the derivative of the right-hand side. And watch what happens when we do this. The derivative of x squared is 2x. Then we have to add to that the derivative of f of x squared. And for that, we've got to use the generalized power rule. It's 2 times f of x to the power of 1 times f prime of x. And then on the right, we have the derivative of 25. That's just 0. So cleaning this up a little bit, we get 2x plus 2f of x times f prime of x equals 0. Let's go back to what we were looking for. We wanted to find f prime of x to answer our question. And look what happened here. We got a little f prime of x right there that happens in an equation. So we could find this f prime of x by solving this equation for f prime of x. Let's do that. The first thing we would do is begin to isolate f prime of x by subtracting a 2x from both sides. So we get 2f of x times f prime of x equals negative 2x. And then we could divide both sides by 2f of x. And we get f prime of x equals negative 2x over 2f of x. And the 2's cancel. So finally we have f prime of x equals negative x over f of x. We've just found our f prime. And we said the answer to our question, the slope of this tangent line, is going to be f prime of 3. So all we have to do to get that is plug in 3 for x in f prime. So our answer is m equals f prime of 3. And that would be 3 over negative f of 3. And to get an answer, we have to think, well, what is f of 3? Look at the graph of f of x. F of 3 equals negative 4. So we get negative 3 over negative 4, or 3/4. So that's our answer. The slope of this tangent line is 3/4, which does look about right. 3 over 4 for rise over run certainly matches our expectations for this slope. The technique that we just applied here is the technique of implicit differentiation. That's what gave us our slope of 3/4. Let's summarize what we did. The process that we just did here, as I said, is called implicit differentiation. And it works this way. Given an equation in x and y, as we had here, if we want to find the derivative dy dx, for example, this f prime of x, as we did here, first of all, regard y equals f of x as an implicit function of x. And that was our first step up here. And in our equation, we regarded the y as a f of x. And we got this step. What did we do next? We differentiated both sides of the equation with respect to x. And when we did that, an f prime of x popped up and we solved for it. F prime of x could also be called dy dx. So step 3 is to solve for dy dx. This process of implicit differentiation that we've outlined here is today's topic. And we'll look at some other examples of implicit differentiation. I want to point out here that in this example, something happened that you're going to see in all of the other examples. When we got our derivative dy dx, or f prime of x, it had an f of x in it. it had a y in it. Y equals f of x, not just an x. And that's essential because in a problem like this one, given an x value, you have two possible y values. You have more than one possible y value because you don't have a function of x. So it would make sense that the derivative, the dy dx that we're looking for, has both an x and an f of x in it, both an x and a y. And you'll see that, and I'll call it out to your attention as we get to it in the next examples. This example involves the graph of the equation x squared plus y squared equals 7 minus xy, which is not the graph of a circle because of this term minus xy. You can find the x and y intercepts here by, say, setting y equals to 0 to find the x-intercepts, and you get x squared equals 7. So the x-intercepts are plus or minus square root of 7, which is about 2.6. And likewise, for the y-intercepts, set x equal to 0, which knocks out this term and this one. You get y squared equals 7. So the y-intercepts are plus or minus square root of 7. And in fact, if you graph this carefully, it looks like this. It's not a circle, but rather an ellipse with x and y intercepts at square root of 7. And you can check that this graph contains the point 1, 2. X equals 1, y equals 2, because if you work out 1 squared plus 2 squared, that equals 7 minus 1 times 2. The point 1, 2 satisfies the equation. So it's on the graph. So the question that we'll answer in this example is to find the slope of the tangent to the graph at this point, 1, 2. So here's the tangent line. The question is, what is its slope? Looks like the slope is definitely negative, somewhere close to -1. But let's find exactly. We'll use implicit differentiation to find the slope. And the idea is that even though the graph of x squared plus y squared equals 7 minus xy is not the graph of a function, it fails the vertical line test, we can make an implicit function, y equals f of x, shown in green here, that passes through the point in question. And we'll use implicit differentiation to find f prime of x. And the answer here will be f prime of 1. Plug in 1 to the derivative, you get the slope. So our strategy, just like before, is to let y equals f of x be an implicit function of the equation, as shown here, and the answer will be f prime of 1. And we'll work this out the way we did the previous example. But in fact, I'm going to work it out two ways. I'll work it out one way here, and then after we do that, I'm going to work it out a second way here. And the second way is going to be shorter to write, but it's really the first way that you'll want to think about this problem in terms of. Whenever you're working a problem like this, involving implicit differentiation with an implicit function y equals f of x, think this, y equals f of x, just as shown here. And that y occurs in the equation x squared plus y squared equals 7 minus xy. So always in these problems, you're remembering that the y that occurs in the equation is an f of x. So let's plug in an f of x everywhere we see a y. We get x squared plus f of x squared equals 7 minus x times f of x. And in the process of implicit differentiation, once we regard y equals f of x, or regard y as f of x, the next step, if you'll remember, is to differentiate both sides with respect to x. You see at this point, both sides of the equations are functions of x. So their derivatives with respect to x have to be equal. So take the derivative of both sides. On the left, the derivative of x squared is 2x. On the right, the derivative of f of x squared, as in the previous example, is 2 times f of x times f prime of x by the generalized power rule. On the other side, we take the derivative of 7, which is 0, but then we have to take the derivative of minus x times f of x, and for that, notice that we have to use the product rule. We take the derivative of minus x, which is minus 1, times the f of x, and then the function minus x times f prime of x. So right there was the product rule. Now we're looking for f prime of 1, and that means we need to have an f prime of x to plug the 1 into. And you'll notice that we get an f prime of x here, but also here. F prime of x occurs in 2 places in this equation. So just like the previous example, we need to solve for f prime of x. It's just slightly more complicated. So the first thing you should do is to solve for f prime of x, isolate the terms that have an f prime of x in them. You could add a minus x f prime of x to both sides to get this term over there. And you could subtract a 2x from both sides to get this 2x over to the other side. And when you do so, you're left with 2 f of x f prime of x plus x f prime of x equals the minus f of x from right here minus the 2x that came across from the other side. So at this point, we have our f prime of x occurring twice on the same side of the equation in 2 terms. So to isolate it, factor it out of these 2 terms. So we get f prime of x times 2f of x plus x. There's the f prime of x factored out. And the right-hand side stays the same. And finally, to isolate f prime of x, to solve for it, just divide both sides by the expression 2f of x plus x. And we get f prime of x is minus f of x minus 2x over 2f of x plus x. So this is our f prime of x. It's our dy dx that we just found with implicit differentiation. Up here we said our answer, that is the slope of this tangent line, is going to be f prime of 1. So to get f prime of 1, you just plug in 1 for x in the equation for f prime of x. And let's check that. The answer is m equals f prime of 1, which would be negative f of 1 minus 2 times 1, divided by 2 times f of 1 plus 1. So there's the 1 plugged in for x. And in this expression, you'll see an f of 1 occurring on the top and the bottom. You have to think, what is f of 1? Go back to your picture here. F of 1 equals 2. Because remember, all of the f's here, the f of x's, are this green function, y equals f of x. So plugging in 2 for f of 1, we get minus 2 times 1 over 2 times 2 plus 1. And that's minus 4/5. So we just found our answer. The slope of this tangent line is exactly minus 4/5, which seems about right. We said the slope looks like it might be about minus 1. Well, minus 4/5 is pretty close to minus 1, so we were pretty much in the ballpark. The slope is exactly minus 4/5 at this point. So we've just answered our question. And I said that I would do this problem 2 ways. We've just done it 1 way on the left. On the right, I'm going to do it again. But here's the idea. Whenever you're doing implicit differentiation, What I've written on the left is what you think. You're always thinking y equals f of x. But as you work these problems, writing that f of x so often gets a little tedious, and you'll want to just write it as a y. So typically, you will solve a problem like this, as I'm about to do on this side. You write it this way. You do exactly the same thing you did. Start off with the equation that you're dealing with, but you just think that y is equal to f of x. That's what you're thinking in your head, y equals f of x, but you don't actually write it as an f of x. You just remember that y is equal to a function of x. So both sides of this equation are functions of x. X squared plus y squared is x squared plus an f of x squared. And as on the other side, you differentiate both sides with respect to x. And in so doing, the derivative of the x squared is 2 times x. And then you have to add on the derivative of y squared, but that's not 2y, because remember, you're thinking that y is actually a function of x. You didn't write it, but you're thinking that. You're remembering it. Y equals f of x. So the derivative of y squared by the generalized power rule is 2 times this function of xy to the power of 1 times the derivative of y. And remember, y is a function of x. Its derivative is not 1. Its derivative is dy dx. So be careful in this step. Even though you didn't write y as an f of x, you're remembering that it is an f of x. So the derivative of y squared is 2 times that f of x to the power of 1 times the derivative of that f of x. It's exactly what we had here, except you just didn't write the y as an f of x. And likewise on the other side, the derivative of 7 is 0, and then you have to add on the derivative of negative x times y, and for that you need the product rule. So that would be the derivative of minus x, which is minus 1, times the second function y, minus, then plus the first function minus x, times the derivative of the second function. And remember, y is a function of x. Its derivative is not 1, but rather f prime of x, or dy dx. And notice that this step is exactly what we had over here. The only difference is, instead of negative 1 times y minus x dy dx, it was negative 1 times f of x. Remember, y is f of x, minus x times f prime of x. And f prime of x is dy dx. So we're exactly where we were right here. So what do we want to do? We're looking for slope in this problem. Slope is given by the derivative dy dx, so we need to solve for dy dx. And this is just going to mirror the steps we had here where we solved for f prime. Get the expressions in this equation that contain a dy dx off to one side, put everything else on the other side. You get dy dx occurring twice, factor it out on this side, and now divide both sides by 2y plus x. And you get dy dx is negative y minus 2x over 2y plus x. And we've just found our derivative dy dx. And notice the expression that we get here is exactly the same as the expression that we got for f prime here. The only difference is we're writing y instead of f of x. But of course, remember, y equals f of x. And we never forgot that when we were doing this derivative. So now that we found dy dx, remember the problem was to find the slope of this tangent line at 1, 2. So we would need to plug in that information into our derivative. And notice our derivative has both an x and a y in it. So there are two things to plug in. an x equals 1 and a y equals 2 to get the slope at this point. So we would write that this way. M equals the function dy dx with the point xy equals 1, 2 plugged into it. That's 1 for x, 2 for y. And doing that in this expression, you get minus 2 times 1 over 2 times 2 plus 1. And that's minus 4/5. So that answers our question. We got the same slope that we got before. The slope of this tangent line is minus 4/5. We did it twice. So we've done this problem in two ways. As I said, I would encourage you to write it the way we did it here. You never write out f of x for y explicitly when you're doing these problems, but you're always thinking it, y equals f of x, as we did it here. And of course, if you would rather do it this way, writing out the f of x, so you don't get confused perhaps, that's fine too. It's a little more writing, but you'll get the same answer, as you see. So we've just finished our example number 2. Before moving on, I want to point out something about this example, about the answer that we got. And let me just erase everything on the right to give myself some room. In this process of implicit differentiation that we carried out here, we got a derivative dy dx. And it was this expression, minus y minus 2x over 2y plus x. And then we plugged in the point xy to get the exact slope. But this derivative, this expression here, it gives you the slope not just at the point xy equals 1, 2, but at any point on this graph. And this is very important. We just found an expression for dy dx. That means the slope of the tangent line to the graph at any point xy on this graph is given by this derivative. The slope of the tangent line is at xy is minus y minus 2x over 2y plus x. So for instance, if you look at this equation, you will see that another point on its graph is the point 1 minus 3 that happens right there. If you substitute x equals 1 and y equals 3, you get 1 squared plus minus 3 squared, that's 10, equals 7 times negative 1 times minus 3, and that's a 10 on the other side. So this point, 1 minus 3, satisfies the equation, so it's on the graph. And it's important to realize that this derivative that we found applies to this point as well. We can find the slope of the tangent line to it. What is its slope? Looks like the slope is going to be different than negative 4/5. Let's find it. The slope of the tangent at the point 1 minus 3, this tangent, would be our derivative dy dx with the point xy equals 1 minus 3 plugged into it. And that's plugging in a 1 for x and a minus 3 for y. And working that out, we get minus 1/5. So this tangent line has a slope of minus 1/5, which of course is different from the slope of the other tangent line. So in doing implicit differentiation, you will get an expression for dy dx, and you should appreciate what that is doing. That dy dx expression, this one, is a machine that finds the slope of any tangent line to the graph of your equation. Just plug in the relevant point, you get the slope. Let's look at another example. In example 3, consider the graph of the equation cosine xy equals sine xy. And in this problem, we want to find the slope of the tangent to this graph at the point pi 1/4. X equals pi, y equals 1/4. And I want to point out, first of all, that this point, pi 1/4, it really is on the graph of this equation, because if you plug in x equals pi, y equals 1/4, these two sides are equal. That point satisfies the equation. For example, plug in x equals pi, y equals 1/4. To the left, you get cosine of pi times 1/4. And that's cosine pi over 4. That's the square root of 2 over 2, as you know, which is also sine of pi times 1/4, sine of x times y. So since this point satisfies the equation, it really is on the graph of the equation. So whatever the graph of this equation looks like, the point pi 1/4 is on it, and that point is about right there. Now, what does this graph look like? It's initially kind of hard to say. It's just some curve on the plane that passes through this point. And I tell you what, the graph looks a little bit problematic. Let's just fake it. All we know so far is it's some curve on the plane that looks like this. It passes through the point pi 1/4 right there. And who knows what it looks like elsewise. We'll just draw it as this squiggly line, which of course is probably not what the graph looks like, but we're just being, we're just using some artistic license here. Even though we don't know exactly what the graph looks like, we can find the slope to the tangent to the graph at the point pi 1/4 with implicit differentiation, just as we did before. We would erase all of this graph except for a little portion of it passing through this point, which is an implicit function y equals f of x. So in this problem, just like before, and all of our implicit differentiation problems, we're thinking y equals f of x, and we never lose sight of that. Every time we write a y, it's an f of x from here on out in this problem. So we'll apply implicit differentiation here to find the derivative, which is essentially the derivative f prime of x. The steps are, number 1, first write the equation. And always we're thinking that the y that occurs there is an f of x. So in this equation, it's cosine x times f of x equals sine x times f of x. But we're going to keep writing the f of x as a y here. The next step in implicit differentiation would be to take the derivative of both sides. But I tell you what, before we do that, let's do a little bit of simplification, even before we take a derivative, just to make this look a little bit better. Let's divide both sides by sine of xy. Now, notice at this point, pi 1/4, sine of pi times 1/4, sine of xy is not 0, so sine of x is not going to be 0 nearby this point. So we can divide both sides of the equation by sine of x, and we get tangent of xy equals 1. So the equation that we're dealing with, cosine xy equals sine of xy, can be re-expressed as tangent of xy equals 1. And it's got the same graph as the original equation. And let's write it that way because this is a little bit simpler than cosine xy equals sine of xy. It's just got one trig function. So here is our equation. And we remember that y is equal to f of x always. And our next step in implicit differentiation is to differentiate both sides of this equation. So the derivative of tangent xy That's the derivative of tangent of x times f of x. So it's a composition. So we've got to use the chain rule here. We take the derivative of the outside function, the derivative of tangent, which is secant squared. We plug in the inside function, x times f of x, and we multiply by the derivative of the inside function. And the derivative of x times y, which remember is x times f of x, we have to use the product rule to get that. The derivative of x is 1 times the function y plus the first function x times the derivative of y. And remember, y is equal to f of x. So its derivative would be f prime of x or dy dx, or in this case, let's just write that as y prime. Denote the derivative as y prime. Save ourselves a little bit of writing. So we're looking for the slope of this tangent, and the slope is given by the derivative f prime of x, or y prime. And you'll see that y prime occurring right here in an equation. So we want to isolate that y prime to get it by itself. So let's do that. Well, one thing we could do here is we could divide both sides by secant squared xy. Now you always have to be careful in an equation. You don't want to divide by 0. But if you look at the point that we're dealing with, we're looking at the graph y equals f of x at or nearby the point pi 1/4. And secant squared of pi times 1/4 is non-zero. So that's going to be true for points nearby this point on the graph. So we can divide both sides by secant squared xy. And we get a really nice simplification. Y plus x y prime equals 0. So to solve for y prime, we just subtract a y from both sides and divide by x. You get y prime equals negative y over x. This is our derivative, y prime, or if you like, f prime of x, that we got with implicit differentiation. So we're looking for the slope of this tangent line at this point. We just need to plug in this point into our derivative. That would be a pi for x and a 1/4 for y in this equation. So our answer is this. The slope m is y prime with the point xy equals pi 1/4 plugged into it. And that would be negative from right here, y, which is 1/4, divided by x, which is pi, or negative 1/4 pi. So there we go. We figured out that the slope of this tangent is negative 1/4 pi. And that gives our answer, which is pretty good for never even having drawn the graph of this function. We just imagined an implicit function y equals f of x. Didn't really matter what it looked like. And we carried out the process of implicit differentiation, and we got an answer. So we're done with this problem, but I want to address one point, and that's the question of the graph of this. We faked it here. We just did a squiggly line and said, let's just imagine that's the graph of our function, or our equation, and we got an answer. We didn't really need the graph. But that's a little bit bothersome, so even though we're finished with this problem, let's take up the issue of what that graph looks like. So the graph of the equation cosine xy equals sine of xy, you could look at, as we did here, as the graph of the equation tangent xy equals 1, which is a little bit simpler. So if we were to graph cosine xy equals sine of xy, that's the same as graphing tangent of xy equals 1. Now, this is interesting because if you try this, it's very hard to isolate the y, to get y equals a function of x that you might be able to graph. But you can analyze this as follows. We're trying to find all of the points xy that satisfy the equation tangent of xy equals 1. And that would be the graph of this equation. If we have tangent of xy equals 1, that means x times y, whatever those two numbers are, have to be such that tangent of their product is equal to 1. And if you think about the unit circle, there are 2 points on the unit circle where tangent is equal to 1. There's pi over 4, then plus an even multiple of pi. And there's also pi over 4 on the other side of the circle, plus an odd multiple of pi. So for example, right here, this point in the unit circle is pi over 4, or pi over 4 plus 2 pi, or pi over 4 plus 4 pi, and so on. This point is pi over 4 plus pi, or pi over 4 plus 3 pi, and so on. And as long as x and y are such that x times y equals pi over 4 plus k pi, here or here, tangent of that is going to be equal to 1. So what we get here is that for tangent of xy to be equal to 1, that x times y, it has to be pi over 4 plus k pi, either here or here on the unit circle, where k is an integer, 0, plus or minus 1, plus or minus 2, and so on. Well, look at that. We could solve for y here. Multiply both sides of this equation by 1 over x, and we get y equals 1 over x times a constant, pi over 4 plus k pi. And that constant depends on what k is. So that's y equals a function of x. And we can graph that. If you think about the graph of y equals f of x, it looks something like this. That's a familiar function. And let's take, to start off with, k equals 0. So in that case, the pi over 4 plus k times pi is just pi over 4. We're graphing y equals 1 over x times pi over 4, which is just scaling the y equals 1 over x function vertically. And that would look something like this. And it passes through this point pi 1/4. It's just the graph of the equation y equals 1 over x scaled by the factor of pi over 4. And you can check that for k equals 0, so it's just y equals 1 over x times pi over 1/4. This point pi 1/4 satisfies that equation, so it's on the graph. But also, don't forget that maybe k is positive 1, so we're adding a 1 times pi right here. So pi over 4 plus 1 times pi, pi over 4 plus pi. It's a little bit bigger than pi over 4, so we're scaling by a slightly bigger number. So if k were equal to 1, we'd get a graph that looks like this. The graph of 1 over x scaled by a bigger number. If k were equal to 2, y is 1 over x times pi over 4 plus 2 pi, and that looks like that. If k is equal to 3 and 4 and so on, we scale by bigger numbers. So the graph of this function, or this equation, cosine xy equals sine of xy, appears to have lots of parts. And we're not even done yet, because k could be negative, like k equals a negative 1. Down here you'd have pi over 4 minus pi, which is negative, and that's scaling the 1 over x function by a negative. So for the negative values of k, you get these other portions on the graph as shown here. So all of this is just, it wasn't really necessary for the problem, but it's just showing you how we could get the graph of this equation. And sure enough, that equation contains this point. We just found the slope of the tangent line at this point. It was negative 1 over 4 pi. which certainly looks right here. And I want to point out, just as I did with the previous example, that this derivative, y prime equals negative y over x, it has an x and a y in it. That expression, that derivative, that y prime, is a machine that finds the slope of the tangent to any point on this very complicated graph. You take any point xy, like say right there, you plug in the x and the y here and there, and you're going to get the slope at that point. Okay, so we've solved this problem in example 3. We've also gone a little bit further and we've looked at the graph of the equation involved, which we didn't really need to find the answer. I want to do one more thing, and that's talk about higher derivatives. And you'll read about this in the text, that in using implicit differentiation, you will find a derivative, like your d dx or y prime. In this case, it was minus y over x. And then you might be asked to find, say, the second derivative. And I want to talk about how to do that. Imagine that in this problem, we got our derivative. Y prime is negative y over x. And then we need to find the second derivative, y prime prime. How would we do that? Well, the second derivative is the derivative of the first derivative. It's d dx of y prime, which is d dx of negative y over x. Now, what are we going to get here? Well, we're taking d dx of negative y over x. Remember, y is a function of x. We're always thinking that in implicit differentiation. So you're differentiating negative f of x over x. You've got to use the quotient rule here. In carrying out the quotient rule, let's bring out the negative and put that out in front. The quotient rule says we take the denominator x, we square it, we put it on the bottom, and then on the top we have the derivative of the top function, which, remember, the derivative of y is not 1 because y is a function of x. The derivative of y is y prime. Then multiplied by the bottom function, x, and then continuing with the quotient rule, there's a negative first function, which is y, times the derivative of the second function, d dx of x. And of course, d dx of x is equal to 1. So we get here y prime, negative y prime x minus y over x squared. And you could look at that as an answer, but you can do better because remember, you know what y prime is. It's negative y over x. So you can replace this derivative y prime with what it equals, negative y over x, and then simplifying that, the x's cancel, you get minus y over x squared, all times minus 1, and that's 2y over x squared. So that's our second derivative, and you can see how you could continue this process to get the higher derivatives. For the equation, cosine xy equals sine of xy with implicit differentiation. So we've done 3 examples today, and of course you want to hone your craft by working other exercises and get good at this. Once you wrap your head around implicit differentiation, it's really an easy process. You've got all the rules for differentiation at your disposal. Implicit differentiation just involves an additional twist. You're looking at y in an equation as an implicit function of x. So in summary, implicit differentiation works this way. Suppose we have an equation in x and y, and we want to find dy dx. First of all, we regard y equals f of x as an implicit function of x. in the equation. Secondly, we differentiate both sides of the equation with respect to x. And finally, solve for dy dx. And in most of the examples and exercises in your text, the variables will be x and y, but bear in mind that they won't always be x and y. They could be other things. Sometimes, and this is especially true in the last section of part 3, the independent variable will be time, so t rather than x. So we might have an equation in t and y, and we want to find dy dt. Same steps. Implicit differentiation would say regard y equals f of t as an implicit function of t, differentiate both sides with respect to t rather than x, and then solve for the derivative, which is not dy dx, it's dy dt. So there's nothing deep going on here, it's just changing variables. But be aware that this happens. So that's it for today. Next time, in lecture 28, we're going to talk about a new technique called logarithmic differentiation. There are no new rules here, it's just a technique. Logarithmic differentiation is going to use implicit differentiation combined with logarithm properties so that we can find derivatives of functions that we previously weren't able to find derivatives of. So get some practice with implicit differentiation and then forge ahead to logarithmic differentiation. And I'll see you next time. Goodbye.